Welcome back to Science Corner.
Yeah.
As always, we love to take these really fascinating scientific concepts and break them down for all of you intellectually curious folks out there.
Absolutely.
And today, we are diving deep into something that sounds like something straight out of science fiction.
Yeah.
It's called the Josephson Effect, but trust me, this is a very real phenomenon.
Oh, yeah,
And it has led to some pretty incredible advancements in technology.
it has.
And it all stems from this interplay between superconductivity and quantum mechanics.
That's right.
It's really amazing. And to help us navigate this intricate world, we have a leading expert in the field with us today.
I'm happy to be here.
Welcome to the show.
Thanks for having me. I'm always excited to talk about the Josephson Effect.
Me too. And we're going to be mainly using the Wikipedia article on the Josephson Effect as our main source for this deep dive.
That sounds good.
So to kind of set the stage for our listeners,
Yeah.
Imagine we have two superconductors,
Right.
materials that can conduct electricity with zero resistance.
Right.
And they're separated by this really tiny, tiny barrier.
Okay.
Now, what happens next is where things get really interesting.
It does get interesting.
So can you walk us through, what is the Josephson effect and how does it actually work?
Sure. So the Josephson Effect describes how a current made up of these special electron pairs, they're called Cooper pairs,
Okay.
can flow through that barrier between the two superconductors even without any voltage pushing it along.
Wow.
Yeah, it's as if the Cooper pairs are tunneling right through the barrier. It's a purely quantum phenomenon.
So we've got superconductivity, we've got quantum tunneling.
Yeah,
That's already a lot to wrap our heads around.
it is.
Can you expand a bit on that quantum tunneling aspect? What is actually happening there?
Well, in the world of quantum mechanics, particles can behave like waves.
Okay.
And just like a wave can kind of spread out and pass through a narrow opening, a particle's wave function can extend beyond a barrier, even if the particle doesn't have enough energy to overcome it classically. So, in a Josephson junction, the Cooper pair's wave functions overlap in the barrier region, allowing them to essentially tunnel through and maintain that supercurrent.
That's incredible. And what's even more fascinating is that this isn't just some theoretical concept.
Right.
The Josephson effect has real-world applications.
Exactly. One of the most well-known applications is in SQUIDs,
SQUIDs.
or superconducting quantum interference devices.
Oh.
These devices are incredibly sensitive to magnetic fields. They're thousands of times more sensitive than conventional magnetometers.
Wow. So how does the Josephson effect play into that sensitivity?
So SQUIDs use Josephson junctions in a loop configuration.
Okay.
And when a magnetic field passes through the loop, it creates a change in the supercurrent flowing through the junctions.
Uh-huh.
By measuring this tiny change in current, we can detect incredibly weak magnetic fields.
That's remarkable. And I'm guessing this sensitivity has led to some pretty impactful applications.
Oh, absolutely. SQUIDs are used in a wide range of fields, from medical imaging, where they can detect tiny magnetic fields produced by brain activity,
Wow.
to geology, where they help map subterranean structures, to materials science, where they can analyze the magnetic properties of materials at an extremely fine scale.
It's amazing to think that something that relies on these quantum phenomena we can't see directly
Right.
can have such tangible effects on so many different areas of science and
It
technology.
really is. And that's just the tip of the iceberg.
Wow.
The Josephson Effect also has a fascinating history full of initial skepticism, groundbreaking experiments, and eventually widespread acceptance and application.
That's actually something I wanted to touch upon. I read that Brian Josephson, who predicted this effect, was only 23 years old at the time.
That's right. He was a graduate student when he made this groundbreaking prediction in 1962, which earned him the Nobel Prize in Physics just a few years later.
It's incredible to think that someone so young could make such a significant contribution to science.
I know, it's amazing.
But as you mentioned, his theory wasn't immediately embraced by everyone, right?
Yeah, even John Bardeen, a renowned physicist who had already won a Nobel Prize for his work on the theory of superconductivity, initially doubted Josephson's predictions.
Wow.
It took a few years and further experimental confirmation for the scientific community to fully accept this revolutionary idea.
It's a good reminder that even in science, new ideas, especially revolutionary ones, can face resistance.
Absolutely.
It often takes time, rigorous experimentation, open-mindedness for those paradigm-shifting concepts to become mainstream.
Yeah, you're absolutely right.
So we've talked about these amazing SQUIDs and the history behind the effect.
Right.
I'm curious to learn more about the different types of Josephson junctions.
Sure.
What are these weak links that separate the superconductors made of?
So there are actually three main types of Josephson junctions, each with its own unique characteristics.
Okay.
SIS, SNS, and SCS junctions.
Okay, let's unpack those acronyms. What do those letters stand for?
Sure. So S stands for superconductor, I for insulator, N for normal metal, and C for constriction.
Gotcha.
So an SIS junction has a thin insulating layer sandwiched between two superconductors,
Okay.
while an SNS junction uses a normal metal as the link.
Makes sense.
And in the SCS step, there's actually a physical narrowing or constriction in the superconducting material itself, creating that weak link.
And how do these different junction types affect their properties and applications?
Well, the type of weak link influences the junction's critical current, which is the maximum supercurrent it can carry.
Oh.
For instance, SIS junctions tend to have lower critical currents compared to SNS junctions. This, in turn, affects their sensitivity and the types of applications they're best suited for.
It sounds like there's a lot of fine-tuning involved in designing these junctions to achieve specific performance characteristics.
Exactly. Choosing the right materials and fabrication techniques is crucial.
Right.
For example, in SIS junctions, aluminum oxide is often used as the insulator, while niobium is a common choice for the superconductors.
Oh.
But researchers are constantly exploring new materials and combinations to improve performance and tailor the junctions for specific applications.
So it's not just about understanding the theory behind the Josephson effect.
Wow.
It's also about mastering the art of creating these intricate junctions with the right materials and structures.
Right.
It's this fascinating intersection of fundamental physics and precision engineering.
Absolutely. And what's even more remarkable is how, despite relying on these delicate quantum phenomena,
Yeah.
the applications of the Josephson effect extend far beyond those highly sensitive SQUIDs we discussed earlier.
Oh, wow.
It even plays a crucial role in defining a fundamental unit of measurement, the volt.
Wait, really? How does the Josephson effect tie into defining the volt? That's a bit mind-boggling.
It has to do with something called the AC Josephson effect.
Okay.
When you apply a constant voltage across a Josephson junction, it generates an alternating supercurrent.
Okay.
And the frequency of this oscillation is precisely proportional to the applied voltage.
Okay, so we've got this perfect relationship between voltage and frequency. How does that translate into defining the volt?
Because that relationship is so precise and predictable, we can use it to create a device called a Josephson voltage standard. By applying a known highly stable frequency to a Josephson junction, we can generate an extremely accurate and stable voltage.
Wow.
This allows us to define the volt in terms of fundamental physical constants rather than relying on less stable physical artifacts.
So essentially, the Josephson effect provides a quantum mechanical basis for the volt,
That's right.
linking a fundamental unit of measurement to those mind-boggling quantum phenomena we've been discussing.
Exactly. It highlights how understanding these seemingly abstract concepts in quantum mechanics can have a profound impact on our ability to make precise measurements in the macroscopic world.
It's a beautiful example of how fundamental physics research can lead to unexpected but incredibly practical outcomes. It's like uncovering a hidden connection between the vast universe and our everyday lives. And there's still so much more to explore about the Josephson effect. Its unique properties, its wide range of applications,
Absolutely.
and its potential to revolutionize technology in the future.
I completely agree. We've only scratched the surface today, and there are many more fascinating aspects of the Josephson effect to delve into.
Well, let's delve in.
All right.
Let's keep going.
Yeah.
You mentioned that we've only scratched the surface.
Right.
I'm curious about this concept I came across while I was prepping for this deep dive. It's called Josephson inductance.
Oh, yeah.
Is that anything like the inductance that we see in coils?
That's a great question. It does show behavior similar to inductance in a coil, but the underlying mechanism is completely different.
Oh,
So in a coil, inductance arises from the magnetic field generated by the current flowing through it.
right.
But with Josephson inductance, it's all about the kinetic energy of those Cooper pairs.
Okay.
You know, those paired electrons that are responsible for superconductivity.
Yeah.
So instead of magnetic fields, it's the motion of those Cooper pairs that creates this inductance.
Okay, so could you give us like a concrete example of how Josephson inductance might be used?
Certainly, one area where Josephson inductance plays a crucial role is in superconducting circuits.
Okay.
These circuits are designed to operate at extremely low temperatures where resistance essentially vanishes.
Right, right.
And because of Josephson inductance, these circuits can exhibit unique and valuable properties like being able to store energy in a very compact space or switching between different states extremely quickly.
So it sounds like Josephson inductance Opens up a whole new world of possibilities in circuit design, especially when working with superconductors.
Exactly. And as we delve deeper into the quantum realm, understanding and manipulating these subtle properties becomes even more crucial.
Absolutely.
For instance, there's another concept related to Josephson junctions that I think our listeners might find fascinating.
Okay.
It's called the Josephson penetration depth.
Okay. Penetration depth sounds intriguing. Is it about how far something can penetrate into these junctions?
You're on the right track. The Josephson penetration depth essentially describes how far an external magnetic field can penetrate into a long Josephson junction.
Okay.
It's a measure of how effectively the superconductors within the junction can shield themselves from that external magnetic field.
So are we talking about a microscopic scale here or something that we could actually see?
It depends on the materials and the current density, but the Josephson penetration depth can range from micrometers to millimeters.
Okay.
To give you a sense of scale, a human hair is about 100 micrometers thick.
So it's still incredibly small,
Right.
but not necessarily on like the atomic level.
Right.
It's fascinating to think that these tiny variations in penetration depth can have a significant impact on how these junctions behave.
Absolutely. These seemingly small details are often crucial in optimizing the performance of Josephson junctions in different applications. And they highlight how a deep understanding of both the theory and the practical aspects of these junctions is necessary to harness their full potential.
You've certainly given us a lot to ponder today.
Oh, good. I'm glad.
We've gone from those mind-boggling quantum tunnels to incredibly sensitive magnetic field detectors.
Yeah.
From the definition of the volt to the intricacies of Josephson inductance and penetration depth, it's clear that the Josephson effect is not just some obscure scientific curiosity.
No, not at all.
It has far-reaching implications and the potential to revolutionize many areas of technology.
And that's what makes it so exciting. It's a field where fundamental physics research constantly intersects with real-world applications. We're still discovering new ways to exploit the Josephson effect.
Wow.
And as our understanding of quantum phenomena grows, I think we'll see even more groundbreaking applications emerge in the future.
I'm particularly intrigued by this AC Josephson effect that you mentioned earlier.
Oh, yeah.
You described it as like a constant voltage creating an oscillating supercurrent, with the frequency of that oscillation directly proportional to the applied voltage.
Yeah.
This concept of a perfect voltage-to-frequency converter seems incredibly powerful. What kind of high-precision applications does that unlock in the world of electronics?
You're right. The AC Josephson effect is truly remarkable in its precision and stability.
Okay.
One area where this is crucial is high-speed communications and computing.
Okay.
Think about the immense amounts of data being transferred and processed every second.
Oh, yeah.
Accurate timing is paramount to ensure that information flows smoothly and operations are executed flawlessly.
Right.
The AC Josephson effect allows us to generate incredibly stable and high-frequency signals, guaranteeing that data transfer and processing happen with incredible accuracy.
So the AC Josephson effect is essentially acting like a super accurate metronome,
That's a great analogy.
ensuring everything stays perfectly synchronized even at those breakneck speeds.
Right, and it's not just about speed and accuracy.
Okay.
This precise voltage-to-frequency relationship is also essential for extremely sensitive detectors.
Oh.
In astronomy, for instance, scientists use instruments based on the AC Josephson effect to detect incredibly faint signals coming from distant objects in the universe.
Wow.
These signals are often buried in noise, but the inherent stability of the AC Josephson effect allows us to tease them out and gain a deeper understanding of the cosmos.
So the AC Josephson effect is helping us explore the universe, improve our communication systems, and push the boundaries of computing.
It's amazing.
It's mind-boggling how something stemming from these quantum phenomena, which operate on such a tiny scale, can have such a massive impact on so many different fields.
And this is why continuous research in fundamental physics is so crucial. You never know what seemingly esoteric discovery might end up revolutionizing the world as we know it. The story of the Josephson effect is a perfect example of that.
It's inspiring to think that a young Brian Josephson working on his theoretical predictions could spark such a wave of innovation that continues to ripple through science and technology decades later.
Yeah, it's really inspiring.
But I have to imagine that working with superconductors and these delicate quantum phenomena comes with its fair share of challenges.
It does.
What are some of the hurdles researchers and engineers face when trying to harness the power of the Josephson effect?
You're absolutely right. One of the biggest challenges is maintaining those extremely low temperatures required for superconductivity.
Oh.
We're often talking about temperatures just a few degrees above absolute zero, which requires using liquid helium for cooling.
Wow.
This adds complexity and expense to any application that relies on the Josephson effect.
So the infrastructure needed to create and maintain these super cold conditions
Yeah,
is a significant hurdle in itself.
exactly. And then there's the delicate nature of the junctions themselves.
Yeah.
They're incredibly sensitive to external noise and interference, which can disrupt their operation. This requires careful engineering and shielding to ensure they function reliably in real-world environments.
It sounds like a constant balancing act trying to push the boundaries of what's possible, while also working within the constraints of these sensitive materials and demanding conditions.
You've hit the nail on the head. It's a continuous back and forth between pushing for higher performance and ensuring practicality and reliability. But that's also what makes this field so exciting.
Yeah.
There's always a new challenge to overcome, a new frontier to explore, and the potential rewards are immense.
It reminds me of that saying, if it were easy, everyone would be doing it.
Right.
And working with the Josephson effect is clearly not for the faint of heart.
Yo, it's not.
It demands expertise, precision, and a deep understanding of both the theoretical underpinnings and the practical limitations.
Absolutely. It's a highly specialized field, but the breakthroughs that come from it often have ripple effects across many different areas of science and technology. And as we gain even greater control over quantum phenomena, who knows what incredible applications will unlock in the years to come.
It's truly mind-boggling to think about, this whole journey of the Josephson effect from a young grad student's theoretical prediction to these far-reaching applications that are literally shaping the world around us. I'm sure many of our listeners are like, okay, so what's next? What does the future hold for this amazing phenomenon?
Right.
Where do you see the Josephson effect playing an even bigger role as our understanding and control of these quantum phenomena continue to grow?
That's a great question, and it's something that researchers all over the world are actively exploring. One area that holds immense promise is quantum computing.
Oh.
Josephson junctions are a key building block for many types of superconducting qubits, which are the basic units of information in a quantum computer.
I heard so much buzz about quantum computing, but it still feels like this futuristic concept,
Yeah, I know.
So how do these Josephson junctions contribute to making this futuristic concept a reality?
Well, the special properties of Josephson junctions, like their ability to exist in a superposition of states, make them ideal candidates for creating and manipulating qubits. And these qubits, in turn, have the potential to revolutionize fields like medicine materials, science, and cryptography by performing calculations that are simply impossible for classical computers.
So by harnessing the Josephson effect, we could unlock computational power that goes so far beyond anything we can even currently imagine. That's super exciting.
It is really exciting.
Are there any other areas where you see the Josephson effect making a big impact in the coming years?
Definitely another area where we're seeing a lot of progress is in high precision metrology, the science of measurement.
Right.
As we discussed earlier, the Josephson effect is already used to define the volt.
Yeah.
But its potential goes far beyond that. Researchers are developing new techniques based on the Josephson effect to measure other fundamental physical constants with unprecedented accuracy, leading to a deeper understanding of the universe.
Wow.
And potentially paving the way for new technologies that we can't even fathom yet.
It's incredible to think that these tiny junctions relying on these strange quantum phenomena could hold the key to unlocking some of the universe's biggest secrets. And it all circles back to the importance of basic research.
Right.
Of pursuing knowledge for its own sake, because you never know where it might lead.
Couldn't have said it better myself. The Josephson effect is a testament to the power of human curiosity and our relentless pursuit of understanding the world around us. And as we continue to explore the quantum realm, I have no doubt that we'll uncover even more amazing applications for this versatile and mind-boggling phenomenon.
Well, it's been an absolute pleasure diving into this topic with you today. You've given us a glimpse into this world where quantum mechanics and cutting-edge technology collide, and I'm sure our listeners are just as fascinated as I am.
The pleasure was all mine. It's always rewarding to share my passion for this field, and I hope we've inspired some of your listeners to explore the world of the Josephson effect further.
And that's what Science Corner is all about, sparking curiosity and igniting a passion for exploration. So to all our listeners out there, keep those minds curious and stay tuned for more deep dives into the fascinating world of science.